Both. Means both. Means both.
Hi, Anna Marie. Feel free to turn on your camera.
Okay.
Okay. The next talk will be a Zoom talk. Okay. All right. Can you spring it out? Great. I think we're ready. Okay. So our next talk will be by Anna Marie Bohmann from Vanderbilt University, and she'll be speaking on higher scissors, congruence, and the K-theory of covers.
Great. Thank you very much. I'd really like to thank the organizers for inviting me to be a part of this conference and to honor Fred. And I had the pleasure of meeting Fred on several occasions and giving talks at Rochester, and he was always an incredibly warm and generous and supportive person, and he's really missed. So it's an honor to be part of this workshop. And yeah. I'd also like to thank the organizers for allowing me to give this talk on Zoom. I had hoped to be there with you all, but I have a 3-month-old. We were hoping to all come. It was logistically rather complicated to get her a passport, so she's stuck in the US for now, and so am I. So anyway, so please bear with me with it being a Zoom talk. I had hoped, as I said, to be there with you all, but it was not possible this summer. So yeah, so as I said, I'm going to give a talk on the higher scissors congruence and the K-theory of covers. This work is joint with Tina Gerhardt, Carrie Malkiewicz, Mona Merling, and Ina Zagarevich. And I'll start by talking a lot about just sort of scissors congruence, and then we'll get a little bit to the K-theory. I've decided that this talk is going to be focused a little more on the examples and a little less on the technical K-theory things, because I think that's fun, and I also think that's more suitable for a Zoom talk where, you know, maybe you don't want to know all the intricate details of K-theory. Maybe you don't want to know all the intricate details no matter what. But here we go. So scissors congruence, what is scissors congruence about? Well, it's about the following question. So when can we take one polytope, say in Euclidean space, and cut it up into finitely many pieces, and then reassemble all those pieces into some other polytope? So basically the question is, if you have 2 polytopes, can I cut them up into some number of pieces, rearrange, and then, you know, end up with the swapping one for the other? And it's clear that there's a necessary condition for this to be possible, which is that my polytopes have to have the same area or the same volume, you know, depending on whether I'm in R2 or a higher dimensional Euclidean space. So here we have a picture of 2 polytopes, this triangle and this quadrilateral, and if my Tixie drawing skills were okay, then I think they have the same area, and I've shown you how you can cut them up into the same pieces and 2 smaller triangles, and then, you know, you can reflect and rotate and translate pieces of one to get the pieces of the other. So these 2 polytopes are scissors congruent, that's what we say. And it turns out, if we're looking at polytopes in 2-dimensional Euclidean space, having the same area is the only criterion you need. It's a sufficient criterion for 2 polytopes to be scissors congruent. So this is like the classical picture of a square and a triangle with the same area, and one way you can cut them up into pieces of the same pieces modular rotations and translations and reassemble one to get the other. And this result, that having the same area is sufficient for polytopes in R2 to be scissors congruence, is due to Wallace, Bolyai, and Gerwin separately in the early 1800s. And it's pretty cool. In fact, it's so cool that there's a beautiful interactive visualization that I'd like to share with you. So let's see if I can share it here. So it's a beautiful scissors congruence demonstration. So you can draw some polytopes, two-dimensional Euclidean polytopes. So here's one. Here's this fun, I don't know, like fun shape. So here's one, and then I'm going to draw another one. Here's another polytope. And the demonstration shrinks them to be the same area because, of course, I didn't draw them that way. And then it cuts each of them up cuts the first one up into triangles, reassembles the triangles into some rectangles so we can understand their area. And then you can cut those up into more triangles that you assemble into the first one. So let's replay this. So here's my two shapes. We've scaled them to the same area. We're going to cut the first one up into pieces or triangles. Then we put them into rectangles so we can see their area, cut that up into two different rectangles of the right areas, and reassemble those into triangles and turn them into the second shape. And this always works. This is an algorithmic procedure that you can do, and it demonstrates why area is a sufficient scissors congruence invariant in R2. So this is pretty cool. This is a beautiful demonstration, and it's really fun to play with. So if you're bored sometime, you can draw really complicated polytopes in R2 and see how they turn into each other by cutting them up. So great. So in R2, this is sufficient. So this is the subject of Hilbert's third problem is, well, we knew this was sufficient and the sufficient condition for scissors congruence invariant in R2, but what about in higher dimensions? So say in R3, are there any scissors congruence invariants other than volume? Does anything have to be the same about my polytopes other than having the same volume in order for them to be scissors congruent invariant? And again, this is one of Hilbert's questions in the 1900 ICM. And it was, I think, the first one to be answered by a student of Hilbert's, Max Dane, in 1901. And he showed that there are indeed other scissors congruence invariants. He constructs something that we call the Dane invariant. And he shows that the cube and the tetrahedron of the same volume have different Dane invariants. Dane invariant is scissors congruence invariant. And so therefore, the cube and the tetrahedron are not scissors congruent. You can't cut up a cube and a tetrahedron of the same volume into different polytopes, fuss them around a lot, and then reassemble one to get the other. That doesn't work. The Dane invariant, I'm not going to give you a precise definition, but it's basically given by summing up the interior angles of faces in your polytopes. That's what it is. In fact, if you take the Dane invariant and volume, this is a complete invariant for scissors congruence in R2, and also there's a higher one-dimensional higher analog in R4. It's a complete invariant there too. But if you go higher dimensional than that, higher than dimension 4, we don't know a complete scissors congruence invariant. So we're not able to say, here are two polytopes in R5. We know they have the same volume. We know they have the same this and the same that and the same the other thing. And so therefore, they're scissors congruent invariant. We don't have that technology. So one thing we can do is we can ask, well, what are sort of things we can do to study scissors congruence invariance more generally? And this is where we get to algebra. So Dane's work, as you saw, was in the very early 1900s. And then around the mid-20th century, the people started working towards a more algebraic approach to scissors congruence. So we can define what we call the scissors congruence group. So we take some geometry X. So when I say a geometry X today, I mean something like Euclidean space of some dimension, or maybe a spherical geometry, maybe hyperbolic. I'll mostly focus on Euclidean because it's sort of the most canonical, and also it's the one where I can draw the best pictures. So that's good. So for some geometry X, we can define the scissors congruence group P of X. And what do? Is we take the free abelian group on polytopes in X, and then we mod out by the following relations. We say that the sum A plus B of two polytopes is the disjoint union. And then we also say that if you take some isometry in the isometry group of X and you apply that to some polytope, then that's the same as before you applied apply the isometry to the polytope. So we identify the image of a polytope under some isometry. Now, a couple things I should say to make this like quite precise is that there's a couple ways you can talk about this disjoint union. Maybe what I really want to say is I want to say that A plus B is equal to the union of A as long as their intersection is measure 0. Something like that, so that I don't have to worry too much about, like if I'm having closed polytopes, I don't have to worry about the edges. And the other thing I should point out is when I say the free union on polytopes in X, I really mean like specific embedded polytopes in X. So like if I have some square right here, and then I shift it along a little bit, a priori, those are different polytopes in Euclidean space. Of course, the identification under the action of the isometry group, that will identify those for me in the end. But a priori, they'll start out as different polytopes. And so they are different elements in generators of my free abelian group before I take X quotient. So it's like a horrendously infinitely generated free abelian group, but I'm imposing some good relations. Okay, and why might you want to define this group? Well, basically by definition, scissors congruence invariance are group homomorphisms out of P of X. So if I have if I look at like volume, then that's a group homomorphism from P of X to the real numbers. That takes every polytope to its volume, and we can see that volume is invariant under these quotients these relations I'm quotienting by, and so I do get a group homomorphism from P of X to R corresponding to say volume. Okay, so here's our scissors congruence group. In fact, we'd like to be a little more general. So in this definition that I've given, we're moving the polytopes by all of the isometries in my isometry group of X. We'd actually like to allow for restricted cases where instead of saying all isometries are allowed, I'm going to restrict to a certain type of isometry. For example, I might want to say I'm only going to be allowed to translate and I'm not going to be allowed to rotate or do any reflections or anything like that. And so that will allow me to sort of move my polytopes by some restricted group of isometries. And for that, I define a slightly more general scissors congruence group, P of XG, where now, again, I'm taking the free abelian group on the polytopes in X. I'm modding out by the disjoint union relation. And now, instead of modding out by the action of all isometries, I just mod out by the action of the isometries in my chosen subgroup of the isometry group of X. So, again, the kinds of G's here we're going to be interested in are often things like translations, maybe the orientation preserving isometry, something like that. And in fact, it turns out a surprisingly useful case is when we let G be just the identity isometry, which is a perfectly valid subgroup of the isometry group. In which case, what we're doing is we're only allowing just for sort of the disjoint union relations. So we're basically saying all we're allowed to do is cut polytopes apart into finer and finer and finer and finer pieces. And we're not allowed to move the pieces around at all. We're just allowed to cut them off. And that's what that case will do for us. So anyway, so we have these scissors congruence groups, and taking homomorphisms out of them gives us scissors congruence invariance. So one way to try to study scissors congruence invariance is by trying to understand this scissors congruence group and homomorphisms out of it. Now, the scissors congruence group can be built out from algebraic K-theory. This is a much more recent result than just the definitions of the scissors congruence group, which date to the mid-20th century. This theorem that you can build scissors congruence out of algebraic K-theory is due to Zakharevich just in the past 10 years or so. So Zakharevich proves that there's an algebraic K-theory spectrum, which she calls K of poly xg. So poly is for polytopes, X is the name of the geometry I'm looking at, and G is this subgroup of isometries that I'm looking at. And this algebraic K-theory spectrum has the property that its zeroth homotopy group is the scissors congruence group in question. So in some sense, this is surprising. This is not algebraic K-theory of like a Waldhausen category or a symmetric nodal category or something like that. This comes from a more general combinatorial approach to algebraic K-theory that Zakharevich built called the K-theory of assemblers. But in some sense, this is also like, this is kind of the thing that algebraic K-theory is designed to do. Algebraic K-theory, philosophically, is about trying to encode relations where you've like chopped something up into smaller pieces and then you like want to record how you can reassemble those pieces back together. That's like the very high level understanding of what algebraic K-theory is supposed to do. So great. So Ina Zakharevich has this theory, K-theory of assemblers, which was built in part to handle this kind of case. And using that, she can show that there's an algebraic K-theory spectrum whose zeroth homotopy group is the scissors congruence group we defined before. And now, since it's an algebraic K-theory spectrum, we don't just get a zeroth homotopy group, we have all of these higher scissors congruence groups given by the higher homotopy groups of this spectrum. So these are the higher scissors congruence groups from the title of my talk. Great. So what do they tell us about? Well, higher scissors congruence groups, we can think of them as encoding what I'll call scissors automorphisms. These are automorphisms of a scissors congruence decomposition. So scissors congruence is really recording, like, when can I take some polytope and decompose it into other polytopes? And one thing that might happen is that maybe there's many ways to get the same decomposition starting with the same original polytope, but maybe you can do that in several different ways. And those will be our automorphisms. So here's an example. So let's look at a very simple geometry, one-dimensional Euclidean space, and let's look at a pretty natural subgroup of the isometries there, which is the group of translations. So we'll look at the K-theory spectrum of polytopes in R1 with the group of isometries we're looking at is just translations. So now polytopes in R1 are not very complicated, they're just little intervals. And so here you can see I have a picture of two different ways to decompose an interval of length 5, that's I5 here, into two intervals of length 2 and length 3. And all I'm allowed to do in order to doing this decomposition is I can chop up the interval of length 5, and then I can translate any of the intervals around. So, and of course, the two natural ways to do it are first you do the length 2 and then the length 3, or if you swap them in the order and you do first length 3 and then length 2. Here's what the picture is. So these are two different ways to decompose the interval of length 5 into the same pieces. And they're fundamentally, we think of these as these should be fundamentally different because one came first and one came second, right? I can't just wiggle a little bit and get from one decomposition to the other, but I am decomposing I5 into the same two pieces. And so this is what gives me a scissors congruence automorphism. And this is, I haven't told you how to build this K-theory spectrum, so you're mostly going to have to believe me that this gives me an element of pi1 of that K-theory spectrum. Okay, and in this case, so this case is comes from work of Zakharevich's original work, and she can actually calculate, in this case, what this pi1 is, and it's the exterior product of R with itself over Q. And this automorphism here gives the element x wedge y, which is maybe slightly less exciting since I chose integer values for the lengths of all of the intervals, but this is true regardless of what the lengths of the intervals are. So this gives us an explicit way to see these elements in pi1 of this K-theory spectrum. So to see scissors congruence automorphism, or in other words, a higher scissors congruence invariant. Okay, well, but more generally, you could ask, we're able to, this is a very simple case where the geometry is very simple, the subgroup we're looking at is really quite straightforward. What about more generally? How could we try to understand the elements of these higher scissors congruence groups, so these higher homotopy groups of K-theory spectra, and tell whether they're trivial or not? And what could we do if we just want to understand more general cases? And so the answer is that what we want to do is build a comparison map, a trace map, to something that's more computable. Algebraic K-theory is not known for being the most computable invariant out there, so we want something a little better. And what we'll use is group homology. So any questions before I move into the group homology aspect of this? Okay. So in order to do this, we need a new approach to K-theory. In particular, what we want to do is group homology and scissors congruence K-theory on the same footing. So make them examples of the same kind of construction so that we can compare them using natural algebraic K-theory maps. And this is what the work I'm focusing on, which is, it's been published, so you can, if you really care about the K-theory details, you can go read it. So that'd be great. So what does our work do? We give a new definition of algebraic K-theory of input data that we call a category with covering families. So what is this? I'm not going to tell you exactly what the definition of a category of covering families is, but here's a little bit about how to think about it. These covering families are analogous to the covers that come up in a growth indeed topology, but they're a little more flexible than a growth indeed topology, which is what allows us to put group homology and scissors congruence K-theory in the same footing ultimately. And what does our algebraic K-theory construction do? Well, it takes our category with covering families and it builds a spectrum in such a way that pi0 of that spectrum is the free abelian group on the objects of my category with covering families modulo the covering relations. So the covering families are going to tell me about how some collection of objects covers another object. And what's going to happen on pi0 is that I'm going to have a relation that says, well, the covered object is equal to the sum of all of the things that cover it. Just as we had in Zacharevich's K-theory of assemblers, that gave us the scissors congruence group as pi0. So here are some examples of categories with covering families and what their algebraic K-theory does. So the first example is the scissors congruence example. If I have some geometry X and I take some subgroup of the isometry group of X, then I can build a category with covering families called PXG. And the category has as objects, it's going to have the polytopes in X. And the covering family data is that a collection of polytopes AI covers a polytope B if there exist isometries in our group G, so that when I union the translates of all the AIs into the GIs, I get the polytope B. So this is really encoding the kinds of covers we see when we chop stuff up and do scissors congruence to them. And indeed, in this case, the K-theory of this category with covering families is the K-theory of the assembler poly XG that Zacharevich defined. And I'll say more generally, if you have an assembler in Zacharevich's sense, then you can turn it into a category with covering families and the K-theories will agree. So it recovers all of Zacharevich's results about assemblers in that way. But you can also get new results. And this second example is an example that doesn't work in Zacharevich's original perspective. And this is the kind of thing that our new perspective, our new approach to algebraic K-theory was designed to work with. So if we have an abelian group A, and we build a category with covering families, which I'll call EA, and the objects here are just the elements of my abelian group A, and we say that a collection of elements A sub I covers another element B, if when we add them all up, if we take the sum of the AIs, then it's equal to B. So that's a new notion of cover. That feels less like, you know, the classical idea of a cover than what you have in the polytopes case, but this also satisfies our conditions. And so you also get an algebraic K-theory spectrum from this. And in this case, it's cooked up so that the algebraic K-theory spectrum of this category of covering families EA is really the Eilenberg-MacLane spectrum of the abelian group A. So you're not getting totally crazy new spectra, but you're recovering the sort of the canonical spectrum you should just hope to associate to your abelian group, which is its Eilenberg-MacLane spectrum. And that's what's ultimately going to allow us to get to group homology. Okay. So, and then we prove the following theorem about our construction. So if you have a group G that acts on a category with covering families, then the homotopy orbits commutes with K-theory. So if I take the homotopy orbits of the category with covering families, so that's CHG here on the inside, that's equivalent to taking the K-theory spectrum of C and then taking the homotopy orbits of that K-theory spectrum. And really you should we prove this directly. You can give it's, you know, a little bit complicated, but not totally undoable to sort of give a nice direct proof where you can see that the homotopy orbits has to commute with K-theory in our case. But you should also compare this result to Thomason has some beautiful abstract results or much more general results about commuting homotopy colimits in K-theory. He wasn't doing this particular approach to K-theory explicitly, so you know it's not quite the same, but But this is very much in the same vein, and if you massage everything around, you can probably deduce our result from Thomason's result, but we have a different and very explicit proof. Okay, and so why is this, why is this good? Well, it's good for the following reason. So if I take some subgroup of the isometry group of X, so G, then in fact, that acts on the category with covering families where I've restricted my group of isometries to just be the identity. So if I think about covers that I'm only allowed to do covers where I just chop things up and I don't allow any moving by isometries at all, well, there's an action of any isometry group on that, just given by like, if I take the whole thing, like the original polytope, and I translate it by some isometry, then it's also going to translate all of the things I cut it up into by the same isometry. And so that gives me a group action on the category with covering families that I started with. So if I initially now no moving at all, I have an action on that space or that category by any subgroup of isometries I so choose. And so what that lets us do is it lets us observe that the K-theory of the category of covering families associated to some scissors congruence with my favorite group G, that's actually the homotopy orbits of the K-theory of covering families with no moving allowed at all. So I can get sort of, scissors congruence with any group of isometries I like by taking homotopy orbits always of the same thing, the same object, which is the K-theory of scissors congruence with no isometries allowed except the identity one. So I can get anything this way. And that's what makes this quite useful. So where do we go from here? Well, now let's go back and try to understand how we can use this new K-theory approach to build us our trace maps to group homology. So as I mentioned before, for any geometry, we always have a group homomorphism from the scissors congruence group of that geometry to R, just given by volume. And in fact, I initially, when I said this, we were thinking about allowing all isometries, so moving our polytopes around by any isometry we wanted. But it's even more the case if I'm not allowed to move them at all, I'm just allowed to chop stuff up. So I have this group homomorphism from the scissors congruence group P of X1 into R. And now volume is preserved by scissors congruence and by these covering families. So this extends to a map of categories with covering families from our category PX1 to the category ER, right? Because what's going on is that the covering families in the target, in the covering category with covering families associated R, those are just telling me like when I add up a bunch of numbers and I get another number. And what's going on in the source? Well, I'm taking a bunch of polytopes and I'm chopping them all up, and then I'm asking like, is the volume of all the chopped up pieces, when I add those all up, does that give me the volume of the thing they reassembled to? And the whole point is that yes, that's how it's supposed to work. I like take a polytope, chop it up into a whole bunch of little pieces, and then in order to get this map of categories with covering families, I need to know that the volume of the big polytope was equal to the sum of the volumes of all the little pieces. And that's exactly what chopping stuff up is supposed to do. Okay, so we get this map of categories with covering families, and then that gives us a map of K-theory spectra. So this is a map from the K-theory spectrum encoding scissors congruence to the Eilenberg-MacLane spectrum of R. And now we can pass to homotopy orbits. So if we take our favorite group of isometries now, G, then we get that the K-theory spectrum for scissors congruence with isometries in G, that's the same as the K-theory spectrum for scissors congruence with no isometries allowed at all, but the homotopy orbits under G. And that therefore maps to the homotopy orbits of the Eilenberg-MacLane spectrum under G. But we know what that does, at least on homotopy groups. So on homotopy groups, when we take the homotopy groups of the homotopy orbits of HR, that's really just giving us the group homology of our group G. Because what are those homotopy orbits? Those are like, the EG smash over G with HR. So that's what we get. We get the group homology of G with coefficients in R. Now, I haven't mentioned this before, but it's important to note that what we get here is we get the homology of G as a discrete group. So of course, subgroups of isometries, those are really nice groups that usually come with some sort of topological structure, like the group of translations that has a beautiful topological structure, orientation preserving isometries of Euclidean space. All of those are topological groups in their most natural form. But when they come to us here, they actually come to us only as discrete groups. And why is this? This is because, when I'm thinking about cutting up polytopes into smaller and smaller pieces and like shifting them around and then reassembling them, almost fitting right back together doesn't cut it for the reassembly. So, if I take some square and I cut it into like two triangles, and I want to like rotate one and then reassemble them to get like a big triangle or something. If I don't rotate the one quite enough, then when I reassemble it, I'm not going to get a triangle. I'm going to get like, two small triangles like attached at just a corner or something. So, almost is not good enough for covering polytopes. Like there's a big difference in translating something to like the spot where two things line up exactly and translating it to like almost there, but not quite. And so that's telling me that the topology of the group G is not coming into play in looking at this group homology. This is a bit of a bummer because the group homology is like less pleasant and less well known in the case where we're looking at these topological groups made discrete, but that's what comes out of the structure. So inherently, what I want to emphasize and what this reflects is that scissors congruence is it's a very combinatorial construction, and it's not nearly as sort of topological as you might hope, at least after we've passed to this algebraicization. All right. So what have we got here? We've gotten ourselves to a trace map into group homology. And I claimed at the beginning, why would we want such a thing? Well, we would hopefully want it because maybe it would be computationally accessible. Maybe it would allow us to understand some things about the source of this map, about these higher scissors congruence groups. And indeed, at least sometimes, it can be computationally accessible. So let's go back to our translation example. So again, the geometry we're looking at is one-dimensional Euclidean space, and the group of isometries we're interested in is translations. So what does our trace map look like? Well, we're going to look at the map on pi1, which is where we were before. So pi1 of the K-theory spectrum, as Zakharevich calculated, this is this exterior product of R with R over Q. And if we look at pi1 of the translation group made discrete, with coefficients in homology translation group made discrete, with coefficients in R, this is R tensor with R over Q. And so we had this scissors congruence automorphism depicted in my picture below here. And Zakharevich proved that this was the element X wedge Y in our pi1. Now one can calculate it quite explicitly that this maps to the element Y tensor X minus X tensor Y in H1. So we have an explicit calculation of what the trace does here. It takes X wedge Y to Y tensor X minus X tensor Y. This is maybe not a total shocker, but it's nice to know that we can explicitly calculate these things. And now we can try for a slightly more complicated example. So now we'll work in R2, so in two-dimensional Euclidean space. So that's our geometry. And I'll focus on the group of orientation preserving isometries, which I'll call SE2. So again, we have volume, which is giving us a trace map from pi1 of the K-theory spectrum here to the group homology now of this group of orientation preserving isometries of two-dimensional Euclidean space made discrete with coefficients in R. And you can calculate that what is this group homology here? Well, it's R mod 2 pi z tensor with R, and this tensor is over Z as I've written it. So what's going on here is that this first tensor factor, the R mod 2 pi z, this is picking up the information about the rotations that were present in the covers that we're looking at. And then the second factor is really picking up the volume part. Okay, and so now we can look at an explicit example of a scissors congruence automorphism and see what it goes to under this trace map. So here's a scissors congruence automorphism. And the first thing I should say is that this beautiful picture is in fact due to Ina Zakarevich, who is a wizard with Tixie, and it's pretty awesome. So what are we looking at here? So on the left-hand side, we have a square with an embedded square. So we have the interior square is a unit square rotated by some angle of theta. And so then the exterior square has side length cosine theta plus sine theta. And over here on the right-hand side, we have the same size exterior square and then the same size interior white square, but the white square has been rotated down. So now it's just like hanging out in, you know, the lower right corner here. And if we look at all these other pieces, now all the other pieces here that are, you know, not in my white square, well, these have the same area because these have the same area of all the colored bits over here and the same area of all the colored bits over here. And so since we're in two-dimensional Euclidean space, we know from the Wallace-Bolyai-Gerwin theorem that if I allow any kinds of isometries, I can always cut up the non-white square stuff and reassemble it and get the like non-white square stuff on the other side. So there's always some way of doing that. But in fact, we can do better than just sort of like cut them up and move them around any way we want. You can cut these up, you can cut all these pieces up, and you can move them purely via translations to get these pieces. So all like, you know, this dark blue triangle here goes to this dark blue triangle here, the light blue square here is this light blue square. All these pieces cut up and reassemble just via translations into giving me sort of the non-white square part on the right. And there's an algorithm for doing this, which is you know why Ina is able to draw such a beautiful picture, is that it's, you know, there's an actual algorithmic procedure for making this happen. But what's the upshot for our trace? Well, what this tells us is that the only rotation that we have in looking at the difference between these two different covers of the big square by all the small pieces, the only difference between in terms of rotations is coming from the rotation of the inner white square. So under our trace, the only part that we're gonna sort of the only thing we're gonna see in the first tensor factor, the R mod Z factor, is what's coming from rotating this white square. All the other like moves that went into our two different, you know, comparing our two different scissors congruence decompositions, all the other different moves are translations, and so they don't show up in this left tensor factor. So ultimately what happens is that this scissors congruence automorphism coming from these two different ways of decomposing the big square into all these separate pieces. This scissors congruence automorphism gives us the element theta tensor 1 in this first group homology. So again, so the theta part here comes from the fact that I rotated the inner white square by angle theta. And the 1 is coming from the fact that that inner white square has unit area. That's why it's theta tensor 1. And so in fact, if you think about it, this shows us that the trace map here is surjective onto the group homology. Because if I look at all the things of the form like theta tensor 1, then it's gonna give me everything in the end. I'm allowed to use any angle theta I want. So cool. So here again, we can see an example where we can explicitly calculate this trace, and that in particular tells us that this scissors congruence automorphism is a non-trivial scissors congruence automorphism, a non-trivial element of this pi1 of the K-theory spectrum of this scissors congruence covering family. So what else can you do? Well, you can do, there's some beautiful work by Carrie Malkiewicz building on our work that gives you some really cool new applications of this. So for this, we want to think not just about the scissors congruence invariant that's given by volume or by area, but there's actually a universal scissors congruence invariant. This is the identity homomorphism between the scissors congruence group, thought of as a scissors congruence group, the home of scissors congruence invariants, to itself, which is a perfectly valid choice of abelian group. Now, this identity homomorphism extends to a map of categories with covering families from the scissors congruence category with covering family to the category with covering families coming from this abelian group P of X1. So that tells us that we have a map of K-theory spectra from the K-theory spectrum of the category with covering families for scissors congruence to this Eilenberg-MacLean spectrum. And then again, we can apply our homotopy orbits construction, and we can see that the scissors congruence spectrum for any group of isometries, this is the homotopy orbits of the one for just the trivial group of isometries, and that's mapping to the homotopy orbits of this Eilenberg-MacLean spectrum for the scissors congruence group, right? So that's the Eilenberg-MacLean spectrum for pi0 of my K-theory spectrum. And what Kerry Malkiewicz does is he uses this homotopy orbits description to identify the scissors congruence K-theory as a Tom spectrum, and then he's able to show that this map is a rational equivalence. So this actually gives him, you know, a way to really sort of get his hands on what's going on with these higher scissors congruence groups and the, at least rationally and in general, it's not just a question, it's not just a matter of the algebraic data of what the higher scissors congruence groups are, but he can rationally identify the whole scissors congruence spectrum. So this is a really beautiful result that comes out of being able to compare these kinds of categories with covering families and their K-theory. And you know, you can get your hands on more scissors congruence invariance, higher scissors congruence invariance, and it's a both a fun tool and a nice calculational tool. And that's what I wanted to tell you about. So thank you very much.